All right. Hello, everybody. It is my great pleasure to announce yet another lecture of Bhishan, alas, the final one. So we wait for all the promised punchlines. It's all yours. Take it away.
Thanks. So yes, this is the last in this mini course. It's also I'm going to tell you about mainly applications C, like classification. And so this is the last in a trilogy of talks I've given this summer about random C-star algebras. The first two in Ben level, the first was about random graph C-star algebras. The second one was about random UHF algebras. Today I'm going to tell you about random inductive limits, not of matrix algebras, which would give you UHF algebras, but of dimension graph algebras. So I'm calling this an application of classification because that's how we're going to approach this. One way of making sense of what do I mean by a random C-star algebra is by classification. So if I have some classifying invariant, I will treat that as a random variable. I will build the invariant randomly, and then I will use it to identify the random isomorphism class of the corresponding C-star algebra.
The Jiangsu is not random.
The Jiangsu it's not random, but it'll be in the class of random algebras I will construct. So it'll be available with some probability, which we will see. And indeed, that is sort of precisely the question that we are going to address. So let me, before I pose the question, let me introduce some terminology. Definition. Let's say that a separable C-star algebra is K-contractible.
Yeah, I apologize for all these cables at your feet, but our next lecture is lecture on K-theory. So I'm sorry, on not theory. So
I'll try to not get myself in a knot. So
Not theorists have tendency to trip themselves on knots. So. Yeah.
So by K-contractible, I mean it is equivalent in K-theory to a point. So separate C-star algebra A, if A is AK equivalent to the complex numbers. So if the UCT holds, if A is in the UCT class, this is equivalent in other ways to having the same K theory as the complex number. So in other words, K0 of A is integers, K1 of A is 0. Okay. All right. Yeah, I have to apologize for this terminology somewhat. It's just something I'm really introducing for the sake of this discussion. I think it's a reasonable terminology. It's what K-contractible means same K theory as a point. But the unfortunate thing is there is already something in the literature called KK-contractible. Which I don't want to confuse this with. So this is not great terminology, but it's just for the sake of this discussion. So do not confuse it. KK contractible in the literature means that KK of A comma A is 0. Right, which I don't know.
and how does it relate to this condition?
It's this would KK contractible would imply in the UCT would be equivalent to both K groups being 0.
All right, so it's a completely different cup of tea.
It's
okay.
Yeah. So, but so I'm not saying KK contractible, I'm saying K contractible. I don't know.
Yeah.
I
All right, and this isomorphism is not necessarily induced by a star homomorphism.
In the UCT, yes,
KK could be very strange.
That's true.
Correspondence.
Yeah, that's true. Yeah, that's true. In the principle, yeah. In principle, it could be. Okay, but that's K contractible, but I want an even stronger condition. So let me say it's strongly K contractible. Again, I don't mean for this to be some kind of lasting terminology. It's just for the sake of the discussion today. So strongly K-contractible. If it has the same K theory as complex numbers, but also taking into account the order structure and the class of the unit. So if K0A and it's positive cone and the unit is isomorphic to so the K0 group Z. The positive cone is natural numbers. Let's agree that 0 is a natural number, and the class of the unit is 1, and K1 being 0. All right. So in this language, the Jacelon algebra is the unique classifiable C-star algebra that is strongly contractible and has a unique trace.
Wait, is it obvious that if you are strongly K-contractible, then you are K-contractible?
Yes, yeah, because part of this is K0 should be Z and K1 should be
See about
In the UCT class.
in the UCT class. Yeah. Say let's
in the UCD classes.
yeah,
That would make sense.
but really and truly, I just want to speak about classifiable C-star algebra. So let's say
Mhm.
K is now in the classifiable class, in particular the UCT pools. But you're right, without the UCT, this would be in principle weaker than being KK. Okay, so Jacelon algebra. That is the unique monofacial. Strongly K-contractible. Topic to be. So I'm going to focus attention on K-contractible objects, and the only bit of the invariant that I have some freedom with is just the trace space. In other words, so the question we're going to ask then is, what is the probability that a random
So how do you distinguish Z from complex numbers?
it's infinite dimensional. That's why
Unique,
yes.
contractible, and infinite dimensional.
Part of the definition of E was it infinite dimensional.
The file were infinite dimensional.
For precisely the reason.
Okay.
For precisely the reason.
Thank you.
Yes. Okay, so here's the question. What is the probability that A is isomorphic to the Jacelon algebra, given that A is strongly K-contractible? Okay, so as I said, the only part of the invariant that we have to play around with on this assumption of strong K-contractibility is trace space. So to make sense of this probability, I need to have some distribution, and what I'm going to do is put a distribution on matriceable showcase indices. And then, as I said, so we're treating the trace space as a random variable, and then be identifying the corresponding isomorphism class of such an object. So maybe first let me maybe just recall. I mean, I know I mentioned this. Just the geometry algebra is built out of these prime dimension drop algebras. So let me just remind you what the dimension drop algebra is. A prime dimension drop algebra is T-star algebra form. That here So it is functions from interval into matrices, MP and Q with some boundary conditions, some dimension drop boundary conditions at 0. So F at 0 is a MP tends to 1 Q, and F 1 is in 1 P tends to M. And prime means that P should be co-prime positive. Okay. So let me call this theorem. So the theorem will say that if we want to address this question, it really does suffice just to ask the question about limits of fundamental drop algebras. So if A in E is K contractible, so K contractible in the presence of the CT just means, remember, K0 is Z, K1 is 0. Then there is some K. Either it's purely infinite. I mean, K contractibility, there's no restriction. It could be purely infinite or still defined. And if it's purely infinite, it has to be a form matrix algebra or infinity. The other possibility is in the still defined case where what I said has to be a limit of time dimension drop algebras. Sorry, I mean this is A is this, or A is isomorphic to some limit of matrices over Z, PMs, QMs.
What is it called? Prime dimension drop algebra, not relatively prime dimension?
Well, why is it called dimensional algebra anyway, not matrix joint algebra?
I mean,
First of all,
for brevity,
we're discussing.
Yeah.
you know, brevity. Yeah, that's a good point. Okay, so. So we don't have much choice about what algebras we're looking at in K, and more if we have strongly K contractible. A strongly K contractible. Then it has to be in this case and with 1.
This theorem.
I mean, I'm going to tell you, it's an observation that follows from classification. Okay, I mean, I would say I prove the theorem, but that's ridiculous to say. It's just an easy observation from classification.
Corollary.
It's a corollary of classification, really. Here's why. Okay, so we know that, as I said, a classifiable C-star algebra is either purely infinite or stably finite. And all we need to do is, because we know we have classification, is just observe that these algebras described in 1 and 2 exhaust the possibilities of the invariant. Right? So in case 1, proof. By the way, what is this class? What is this K? This K is just the class of the unit. So that's what we're in. So either A is purely infinite. And in that case, the Elliott invariant is just reduces to the K0 group and the K1 group. So this is, well, it reduces to K0A, the class of the units, and K1. The order structure is not enter into it. In fact, K0A plus is the whole of K0A. Right. And then by assumption, this is integers. This is K, it's some K in Z, some K. and this is 0. But this is isomorphic to the Elliott invariant.
The position of the positive cone inside K0 is irrelevant.
In the purely infinite case, yeah. I mean, the positive cone is the whole thing, in fact. Yeah, it's degenerate in that sense, in the purely infinite sense.
It's an algebraic group. How this
Uh,
to a positive cone?
why not? I mean, it's,
Mhm.
I see no a priori reason why it couldn't happen, and in fact, it does. It is the case. Okay, so that's why. So you just choose this K to be the class that
I would expect N to a cone. But you said
you would expect. No. It's for purely infinite algebras. It really is. It's really easy. It really, yes. It really is. Really is.
Generated by one? No, not necessarily.
Not necessarily. Yeah, I guess I'm just realizing. I'm sorry, I'm just realizing that maybe this could be negative. The class of 1 could be -1, I guess, but then we have an automorphism. Yes, a group automorphism. It's not true. No. Yes, I guess in my case, multiplication by -1 would be group automorphism. Yeah, okay. I don't think this is such an issue. Yeah.
well, it could be negative.
It could be negative, I'm guessing, but the mark from Z to Z, that's multiplication by -1. This is an additive group isomorphism. So this means it lifts to an isomorphism of the algebra by classification. So there is some automorphism that sends. No, well, that can't be right. No, that can't be right because it has to pick the class of unit. Okay, I need another. This is an interesting point. I should ponder. Yes, point would be negative possibly. All right, but the homework for myself. What if? -1. I mean, this is not. We're not interested in the purely infinite case at all. I'm shortly going to restrict it strongly. K-contractible ones who are in the stably finite setting.
What is strange here is that the K could be not a generator.
Yeah, that's possible. That's possible.
Yes, but it's some strange phenomenon.
So, you know, all right, let me put a pin in this, and let's move on. Okay, so either it's purely infinite or it's finite. So in which case, okay, so we have, in fact, we must have A0 of A plus is N, agreeing that 0 is a natural number. Right, so just to return to the definition. So I said in the K-contractible case, all I'm assuming is that the K0 group has to be the integers and the K1 group has to be 0. But I'm saying that in fact, we from this we can deduce that the positive cone has to be N in the stably finite case. And this is because of weak unpreparation. This is by weekend preparation. Weekend preparation in an ordered group means that an element X is positive if and only if NX is positive for some entity. And big one.
What is the class of the unit?
The class of the
Stable finite space.
okay, so again, K.
But by asking, I mean, n is just a number here. It's n is a natural number and it has to be at least one.
But it'll still be the class of the unit will still be represented by some K. So let me clarify. So note for any trace. We have the trace of the unit has to be, it is in fact one. The trace, every trace is a state, trace of one, which is positive. One consequence of being a stably finite stable C-star algebra is that the ordering on the K0 group is determined by the behavior of the traces. So if the trace of some element in the K0 group is positive for all traces, then this has to be a positive element. So this tells me that one, which is going to be K times some generator. So one will be represented by some class K. So one, the class of one is K times one, has to be positive. Okay, so I mean, one is just the generator of the group. So this is just the class corresponding to it. So the class of one has to be positive. But this tells me that the generator has to be positive by weekend perforation. This tells me that one has to be bigger than zero. So this tells me that the positive cone has to be the natural numbers. There can't be any sort of gaps. It can't be like 2 times the natural numbers. So this tells me that A0 A plus the natural numbers. Okay, so this regularity properties of the C-star algebra and interactability tells me forces the order structure on me. And so again, we would just a similar reason as for the O infinity, the pure infinite case here. We just make a similar observation by noting that. So finally, this is a theorem proof in Jacelon's original paper. Even there exists a simple limit B of the bond of some Z in appearance such that the trace space of B is isomorphic to the trace space of A. We've got. Okay, what is this simple inductive limit? Inductive limit that is simple. That is a simple C-star algebra. That's all.
Okay. Okay.
I know. I understand the confusion, but yes, inductive limit that gives a C-star, a simple C-star algebra. It's like, okay, so this tells me that the LA variant of B, these are sort of designed, my models for being strongly K contracted. So this is
And the mappings in this system are irrelevant.
irrelevant. Yeah, there's some unit cell star homomorphisms which can be described fairly concretely, but irrelevant.
Not necessarily injective.
Yes, injective. Yes,
Must be injective.
they must be injective because these are projectionless. That in fact forces injectivity.
Any map of projects or
It's essentially because any quotient. I wouldn't know. I don't know if I'd say it quite in that generality, but in this kind of context of maps between subhomogeneous C-star algebras that are projectionless, yes, because the algebras are projectionless, but any quotient would have non-trivial projections. That's why. Okay, but this is not, it's not so important. I mean, they are injected by design or by necessity. Okay, so the electric variant of B is, I'll just say, size the electric variant of B. All right, so I mean, the long and short of it is these algebras we described, they model feature algebras that exhaust the possibilities of the invariant. So if we want to answer this question about probability distributions on this notion of strongly K constructible Caesar algebras, it's enough to look at. Not only is it enough, but you have no choice but to look at limits of prime dimension algebras. Okay, so
It's the standard form.
exactly.
Such an
Absolutely. Yes, exactly. All right. So maybe, as I said, maybe I'll just write this down. So we will, describe probability distribution. Or in fact, I'll tell you about maybe three families of probability distributions on the collection, on the set of isomorphism classes. Mechanical alterations. Hence on these strongly alphas. Right, so we'll build the random simplex and then identify the isomorphism class of the corresponding Caesar algebra. Okay, so to do this, I'm going to use this Lazar-Linden-Strauss theorem, which I mentioned a couple of times. I'll re-describe it to you. It's the one that says that every simplex, every matriceable showcase simplex, is a projective limit of finite dimensional ones. Theorem. Linden-Strauss. So every matriceable case delta sig is isomorphic to projective limit delta delta n psi n. So where it's delta n yeah, okay. Delta n is the n simplex, right? As combination E 0 n E and n simplex, n-dimensional simplex, and psi n from delta n to delta n minus 1 is affine, continuous affine surjection. It's an affine surjection.
And this is not, let's say, the last generation, nothing like that.
So, sorry,
There are some subjections between synthesis,
yeah,
like the generations. And this psi n is none of them.
but what do you mean by generations? I'm not
The
sure.
generations.
Meaning, it's,
There are some geometric maps
uh-huh.
of collapsing some faces. For instance.
Well, in fact, maybe, so it is a collapsing map, so, maybe I describe it to you, so it's like this. So I think of,
It's completion map. Between matrices.
meaning, let me describe it to you, and then you can tell me if it is what it is, because maybe I'm just not
Or
familiar.
maybe not, because if you have a triangle,
Yeah.
you can collapse it in the way that this vertex go to the middle of.
Yes, that's allowed. Yes, absolutely. Yes. I see what you mean. Yes. So if in fact, one of the probability distributions we'll consider maybe would be one of these simplex. We demand a vertex gets collapsed to another vertex. And this will give you a certain kind of structure, but it's a restriction. But we'll consider this.
And what do you mean by this affine condition? What's,
So these are convex sets.
yes,
So I just mean it preserves convex combinations.
Convex combinations go to convex conditions.
Yeah.
With the same
Barycentric coordinates.
okay, thank you.
So I think of this as the base of delta n. And this is what you might call a collapsing map. All right, so maybe okay, so it's the zero simplex. It's the one simplex. Okay, I have no choice about what the map is from the one simplex to the zero simplex. Everything just gets sent to this point. The next I have is two simplex. Okay, maybe this. The base gets fixed. So the red point gets sent to this red point. The blue point gets sent to this blue point. And this green point gets sent somewhere in the middle. Somewhere. It could be the endpoints, but in general, it could be somewhere along the way. Right? And then it just so I just extend affinely. So I define, in other words, psi n of a convex combination, the sum of the convex combination be sum of lambda I e I n I equals 0 to n is lambda is sum I 0 to n lambda I psi n e I. It's enough to know what happens to the vertices. Just extend affine.
Is the choice of this psi important?
Yeah, absolutely. In fact, what I will make precise now is what's important is these choice of points that we collapse the extra vertex to, and if we collect, so each point that we collapse to has some barycentric coordinates. So let's say.
Why is this letter sum a convex combination? Now that one of the vertices is in the middle.
Sorry, say again.
You told me that affinity, being affine for a map, means that it maps convex combinations. Yes, surely. I look at this triangle, these vertices are these E's, and you have a convex combination.
Yeah.
But now when I collapse one of these vertices into this middle of the interval, now there is still a convex combination.
It is, but the difference is that these images of these vertices,
yes,
maybe are not affinely independent.
but they still give convex combination.
Still a fine map.
Yeah.
Thank you for clarifying.
Convex.
Yes.
Absolutely, right. Okay, so right, so in other words, so psi n fixes its base, fixes the base delta n minus 1 of delta n, and sends this extra vertex e and n to some point in the middle, which we describe by coordinates. So I equals something to something, A, I, N, E, I'm going to N minus 1. I guess it's going from 1 to N. So I mean, so these are just the arithmetic coordinates. Of the collapse. And then if we collect all these barycentric coordinates into a matrix, in fact, an upper triangular matrix, we call that a representing matrix for the simplex. So the matrix Aij, Ij in N. So the upper triangular. Okay, so all I'm saying is, but the first we have no choice. The first it was just A1, 1. We had to collapse to the unique point in the zero simplex. The second, we have A1, 1, then A1, 2. My numbering is numbering. Sorry, it should be.
Why you label them I from 0 to N minus 1?
I'm going to confuse myself if I start doing that. It is what it is. Let's just live with it. So this would be so the N is fixed. So the N is fixed. So this would be A1, 2, and then A2, 2, right? Okay. Then A1, 3, A2, 3, A3, 3, etc. Okay. So this is called a representing matrix for the simplex. This is called a representing. Or simplex delta. All right, and then okay, so the upper triangle as I said. We can identify the collection of all representing matrices with the product of all finite dimensional simplices. So this is just some point in the zero simplex. This is some point in the one simplex. This is some point in the two simplex, and so on and so on. So we identify the collection of all representing matrices. With the product from n 0 to infinity of the n simplices. Okay, just we send a matrix to the product of the columns. That's how we get it. So we make this identification as depth. And also as measure spaces. What I'll do is I'll put some product measure on this. And this will give me a measure, a probability measure on this collection.
So on every factor you have a normalized Lebesgue measure.
A normalized Borel probability measure.
A probability measure, not necessarily.
Not necessarily big, although it could be anything. I'll consider three possibilities. Set and as measure spaces. Once we equip this product with some product measure, and 0 to infinity of some Borel probability measures UA. All right. And then so we have a map from representing matrices to the collection of simplices. Okay, so each representing matrix gives me this matrix of numbers. This tells me what the collapse points are. So this matrix describes what the connecting maps are. So I have a map, and therefore it constructs a simplex for me. So I have a map from representing matrices to simplices. and I will just push forward the measure on here onto the collection of simplices. So that's how I get my probability distribution on simplices. All right, maybe I write that down. So we use sort of the map from representing matrices to the collection of isomorphism classes of syntheses, triangle showcase syntheses, pushes the measure, its product measure, to a probability measure. On the collection of syntheses. I should say, so this map is definitely not one-to-one. There are, it's infinity to one, in fact. So,
So it's not the proper map.
right. I mean, it's infinity to one for one. Here's one basic reason why it is. If I have two representing matrices which are not the same but are asymptotically the same, meaning that the numbers get suitably closer and closer together in some way that can be made precise, then they will describe in the limit the same simplex. So for that simple reason, it's infinity to one, but it's even more complicated than that, because that doesn't even begin to describe the possible pre-images of given simplex. You can have all sorts of different representing matrices, but whatever, that doesn't matter. Just using this map anyway, it's going to push forward this measure. All right. Okay, so maybe now let's address the question: what are we going to? What are some number candidates for these events? So I mean, okay, we need. I'm going to tell you three specific cases that are quite special, and I'm telling you about these special cases because I can tell you what the answer is in these cases. I mean, if we're a bit wild and we allowed any old mu-n's, it might be a bit difficult to control what kind of distribution we get on the limit. But anyway, let me describe just some basic cases. So we'll consider. All right, first of all, case one is where we have no randomness at all. So let's just say we decide that we're going to collapse right to the center of mass. So mu-n is the point mass. At the center, which is the average of the points. So 1/n+1 sum I equals 0 n e I n of delta n. It's spread. Right, so with this setup, which is all the time collapsing to the middle, no randomness at all. Secondly, we do what was mentioned earlier. So we demand that we collapse the extra vertex to one of the other. It has to collapse to another vertex, but we choose one at random. We take the uniform counting measure on the n. Yes, the n vertices. So the uniform counting measure.
Random degeneracy.
Yeah, I suppose so. Yes, yes. Although I guess I was not aware of this term. Uniform complement. On the yes, it's okay, right. So it's it's the collapsing point, so it should be on the n+1. Yes, n+1 is delta n. So in other words, it is 1/n+1, the sum I equals 0 to n of point mass times E I n. Okay, so that means that the next simplex, the delta n plus 1, if you like, will get collapsed. The extra, so the base all the time is fixed, but the extra vertex gets mapped to one of these vertices of the base with equal probability. And the third one is a bit more involved to describe. Essentially, what I would like to do is do the natural thing of taking just the normalize the big measure on the simplex. But I need to be a little bit more careful about that. So let me describe it like this. So let me write n to be n plus 1 over 2. You know, the sum of the first n natural numbers. I'm going to describe to you what mu Sn plus I is for I between 1 and n plus 1. Right, and then so this will give me a sequence of mu's, and this will describe all of them. Okay, so this is describing mu nn plus 1 over 2 all the way up to mu n plus 1 n plus 2 over 2. Right, and then I can iterate through the procedure. So what this is, it'll be the normalized big measure.
The Canadian spelling of center is like the British one, right?
Yes, yes, it's true. Normalized big measure on delta. So I'm going to do it. I'm going to start with doing a normalized big measure on delta n itself, but then delta n minus I, is that what I've done? Something like this.
Piotr, may I ask a question? Bhishan, I didn't quite catch how a map between two simplices, two finite dimensional simplices, mapping one onto the other. I didn't quite catch how that can be described by a measure.
So it's right. So it's not described by measure. It's described by a column vector. So it's described by one of these column vectors here. And then what it's a good question because I guess I didn't.
Oh, okay. So but then but still you're talking about a measure.
Yeah, so what I'm going to do is I'm going to choose these vectors at random according to the measure. So I will choose a random vector in the one simplex according to the measure mu1. Then I will choose a random vector in the two simplex according to the measure mu2. And I'll choose. So I use the measures to randomly choose collapsing points. That's how I.
Okay, but are you you're assuming that the map is surjective, but what's the collapse point?
The collapse point is this randomly chosen vector here. So all the time the maps, these psi-ns are described all the time by fixing the base of the simplex. So that's always the case. And then this extra vertex is sent to some points, some intermediate points in between. And then, so all I'm doing is I'm randomly choosing this extra point that the vertex in the extra dimension gets sent to. So I have no choice for the base, and then the extra vertex is some random point.
So are you maybe you're assuming that the each simplex is just one dimension more than the the earlier one.
Yeah,
okay,
I am.
That makes sense.
Yep.
Okay, thanks. Yeah.
Sure. And that's a good point, in fact, because the Lazar-Lindenstrauss theorem says that we can always do that. Yeah. So it's every simplex can be described in this way.
Okay. Well, thanks very much. Sure. By the way, I guess extreme points go to extreme points, or at least every extreme point is if it's a surjective map between simplices, then every extreme point is the image of an extreme point. Does every extreme point map into an extreme point?
No. But it is true that every extreme point in the image is
Convex combination of extreme points.
okay. Yeah, but
So this map can be very easily described. You have standard degeneracy maps between simplices. And then you are taking a convex combination of these standard degeneracy maps. And these columns in this matrix, these are precisely these coefficients of these convex combinations.
Yeah, okay, so I understand a little better now, I think. Yes, so sorry to hold you up, thank you.
no worries. Okay, thank you.
Sure.
All right, okay. Right, so it's the middle of describing this, so maybe yeah, as I said, I would essentially just like to say that UN is the normalized big measure on delta N. Morally, that's what I want to say. But in fact, what I'm going to say is I'm going to take the normalized measure on delta N, then on its base delta N minus 1, then on the base of that delta N minus 2, all the way down to delta 0. So I'm going to take normalize the big measure on the convex combination of E0N all the way down to En minus I plus 1 N. Okay, let's think about what this is saying. So if I is 1, this is the convex combination of E0N up to ENN. So this is the whole thing. So the measure mu Sn plus 1 is normalized Lebesgue measure on all of delta N. So in other ways, what we're doing is so we randomly sample. Okay, so the first one is delta N. Then we're going from E0N up to, so I is 2, N minus 1, comma N. So this is the base of delta N. So then we randomly sample the next one, delta N minus 1. Then we do one less, delta N minus 2, all the way down. Maybe even this. Okay, so I'm taking a uniform random sample of the simplex delta N, but just remembering all of its bases, all of the previous stages. So I'm taking a, if you like, a uniform random sample of the structure delta N, comma, delta N minus 1, comma, delta N minus 2, all the way down. All right, I'm doing this for a reason, because I would like to get a certain kind of simplex in the limit. I want to say with probability 1, when I do this kind of delicate sampling, I'm going to get a certain simplex in the limit. Maybe no prizes for guessing what simplex I'm after in this, but we'll see we'll see shortly. Okay, so we have these three cases I'm considering. No randomness in the first one, randomly collapsing to a vertex of the base in the second one, and this kind of delicate random sampling of simplicities in the third one. Okay, so this is how we are going to build our random simplices by choosing these random collapse points. But in fact, I'm going to allow for a second kind of randomness. So in fact, we allow not just for random collapse points, but I'm going to allow for a random progression and a random sequence of simplex dimensions. Random, but random simplex dimensions. And the way I'm going to do this is via random walk. So in the In the Lazar limit trucks that as George flagged up, the simplex always goes one higher in dimension in this sequence. But by taking a random walk on the natural numbers, I'm going to just describe the simple case where I can either jump up one or jump lower than jump down by one. You could imagine doing something more complicated to allow for jumping up by some k and down by some l, whatever. But then again, the more complicated you go with that, the more complicated it is to compute with things. But in a sense, which maybe I'll return to, it doesn't really matter. I will return to that point whereby it doesn't matter if we did something simple-minded like this or more complicated. But let me first.
Sorry. So if you go down,
Yes,
in the dimension,
yes,
your degeneration is always a random, say, degeneration.
yeah.
If you go up,
Yeah.
is it what I'm going to say?
Yeah. So in fact, the way I'm going to describe it is it's going to be deterministic.
It's the random phase.
Hi, this is a very good point, which I sort of wish I had considered, because that would be very natural. But in fact, I'm going to just demand it just be the base inclusion. So if it goes up a dimension, it's just going to be the map. It has to include into the base.
So these are always the initial phase.
Yeah, exactly. Yes. But you raise a good point. You might think it would be more natural to do a random phase. I suspect as long as we set things up properly, it shouldn't make too much of a difference anyway. I will see. It's kind of classical probabilistic setup that I have. What we will see happening is that, things are going to happen with probability 1 or probability 0. You're going to be able to reach some structure. And I suspect that if we did allow for this random phase inclusions, it would still be the same kind of situation. Okay, but anyway, random walk. So what I will do is we take a simple random walk. Simple just means I can only move up by 1 or down by 1, but I'll make this more precise shortly. Simple random walk, yn on.
But I have another question though.
Yeah.
How can you have it if it's one dimension lower? How can you have a surjective map? Are you dropping that?
Yeah. Yes, I suppose I am. Yes. Yeah.
No, sorry. Huh.
Yeah.
Okay.
No, that's a different. Yeah.
Okay.
Yeah. All right. So random walk on the natural numbers. So with some initial distribution.
But what's the collapsing point then in the representing measure if you
Yeah.
projected anymore?
Yeah, I mean it's a good point you raise. So what I'm going to do ultimately is I'm going to build this projected limit delta yn psi n triangle from delta n to delta yn minus 1. Right.
Sure.
If yn is yn minus 1 minus 1, I guess. So if this map is going 1 dimension higher, then I'm just going to demand that this psi is the base inclusion. So psi n is the base inclusion. Of delta yn in delta yn minus 1. I'm just going to make it deterministic. So there is no collapsing point because there is no collapsing in this situation. I'm just so I would so if I'm moving from a triangle to a tetrahedron, then I just map this triangle to this space here. I just include it here. So what I will be constructing is a random projective limit of finite dimensional simplices with affine connecting maps, not necessarily subjective. Does that help?
I don't understand this.
Uh-huh.
What is written? Yn is equal to 1, yn minus 1
So
minus
if,
1.
if,
If,
yes.
what does it mean?
Just what we were saying just now. So I'm saying that if I'm so this psi n is some map from the yn simplex to the yn minus 1 simplex. So I'm saying that if yn is smaller, that means I'm jumping down.
So this is
jumping up
dimensions.
Yeah, yes. So these numbers are, so y is some integer, is some positive integer, yes. So maybe yn is 3 and yn minus 1 is 4. So I need to describe for you some map that's connecting the 3 simplex into the 4 simplex. And I'm saying just send it to the base.
Okay.
In that case, if we're jumping lower in dimension.
Okay.
If we're jumping higher in dimension, we do the procedure I described before, have a collapse.
So this sequence is not necessarily monotone.
Exactly. Yeah, it need not be. Yeah, because so I was maybe in the middle of describing exactly what the sequence is. So maybe I finish it. So we take a simple random walk with initial distribution II and transition matrix. Let's say half of pi. So what this means is the probability that the starting point of the walk is I is from I is pi. And so what I'm describing to you, in other words, is a discrete time Markov chain. And which means that which means this, right, the probability that yn is a given that yn minus 1 is I is this matrix of this transition matrix ij, and the fact that I'm demanding it to be a simple random walk means, as I said, we can just jump up by 1 or jump down by 1. So it'll either be so with probability p, it jumps which way do I want it? Up. So if j is I plus 1, with probability q, which is 1 minus p, it jumps the other way. P is I minus 1 and 0 to everything else. All right, I'll draw a picture on the next slide. Maybe let's just pause and stare at this. Okay, so I have some these yns is my position on the natural numbers at time n. At time 0, I start at some position I with probability pi I. Okay, and then at time n, my position is only determined by my position at time n minus 1. Nothing that happened in the past. That's the defining property of a Markov chain. Your next move is determined entirely by your present position, not anything you've done in the past.
Are you going to speak about martingales?
No, I'm not.
The Markov chain.
It's a discrete time Markov chain. What I described. Right. Okay. So maybe I draw a picture. We have our states 0, 1, 2, 3, and so on. So if I'm at position 1, I can either jump to position 2 with probability p, or I can jump to position 0 with probability q. Similarly at 2, I can either jump to position 3 with probability p, or jump down to 1 with probability q, and so on. Okay, I need to describe, so 0 is a special point, it's the boundary. There are a couple of different ways I could set this up, but let's just say for the sake of this discussion, that I demand that 0 is what's called a reflecting barrier. Which means that if if I ever do reach position 0, then with probability 1, I can bounce right back to position 1 in the next step.
And so there's a probability that yn is 1, given that yn minus 0 is 1. All right. The 0, 1, 2, 3, in fact, means y0, y1, y2, y3. Or what is it?
No, so y0 is the position, yn is the position at time n. So the xn is the
Yeah.
time parameter. So yn could be, so y2 could be 6 million.
These are really natural numbers, and now we have random walk.
And you can go this way. That
Yeah.
way.
Right. Okay, so maybe I'll just say this, yn is, as I said, it's, in fact, it's not just any old Markov chain, it's an irreducible Markov chain. Irreducible discrete time Markov chain. Irreducible means that, okay, maybe I say this, so for any ij, there is ij, if y0 equals I, then there is some non-zero probability of yn being j for some n. Non-zero probability of yn equals j for some n. In other words, I transition between any two states with non-zero probability. That's what irreducible means. And that it's a fact about irreducible Markov chains that either so this is why what I'm about to say is why I said it doesn't really matter whether I had set up a more complicated random walk where I allow not just for one-step transitions, but n-step transitions, or maybe over a grid or something. It doesn't matter, because in an irreducible Markov chain, what's true is that either every state is recurrent or every state is transient. Recurrent means with probability 1 it is visited infinitely many times. Transient means with probability 1 it's visited most finitely many times. We'll break this down. So this is a theorem, I guess, that a basic fact about the theory of Markov chains. So for an irreducible Markov chain, it's true that either every state,
the cutoff.
yeah, every state is recurrent. This is it. Infinitely often with probability 1. Or every state is transient. Meaning visited finally often with probability 1. It's most, or maybe not at all, finitely often. Probability. All right. And in fact, so we know which is which for this particular Markov chain that I have here. Well, let's think about what we should expect. If P is larger than Q, this is saying that I have a tendency to head off to the right more so than I have to return to the start. So our expectation is that if P is larger than Q, it'll be the transient case, and the other way around. If Q is larger than P, then I expect to be in the current.
How about P equal Q?
So P equals Q, it is in fact recurrent, it is, but it's what's called null recurrent. Null recurrent means that, yes, with probability 1, I visit every state infinitely often, but the average return time between visits is infinity. So yeah, that's the special thing about P equals Q.
Okay, very interesting.
All right. So maybe I say, okay, and this is very, very practical. By results of Carlin and McGregor, for example, back in the 50s, I think. So our walk YM that I described is transient if P is bigger than Q and current if it's bigger than or equal to P. Okay, in fact, all right, what I've presented here is a sort of simplified version of what you could do. I mean, here are a couple ways we could think about tweaking this. First of all, I demanded here in this kind of a toy situation that all of these probabilities are the same, right? No reason that I need to do that. I could allow for them being varied, and then there are some conditions about how they behave asymptotically that tell me when I'm in the transient case, when I'm in the recurrent case. So that's the first thing that we could think tweaking. Let's not get into that here. Second thing is what's happening at 0. So the way I've set it up here, we're always going to have an infinite random walk. Even if I get back to the start, I go right back out again. So walk is always infinite. But what I could think of doing, but I won't go into it here, is I could introduce not a reflecting barrier at 0, but I can introduce a absorbing state. Let's call it -1. So if I reach 0, then with some probability that's less than 1, I will go back out, or with some other with the complementary probability, I will go to my absorbing state and stay put. So the walk I could set things up so that the walk does terminate. All right. Remember, what am I trying to capture with this random walk? I intend for the position of the walk, this yn is intended to be the dimension of the simplex in my inductive sequence. So if I allow for this absorbing state, then in other ways, I'm saying I'm allowing for the possibility of constructing a finite dimensional simplex, of stopping my inductive limit at a certain point. And then I could take the biggest simplex dimension that I reached, and I could demand that to be the finite dimensional simplex that I constructed. And then I could even compute what the probability of that happening is. It's doable. Okay, but that's not what I'm doing here. So if we are having an infinite random walk all the time, so we are certainly constructing an infinite sequence of synthesis. So now just to sum up then our situation. Sum up. The random situation we find ourselves in. So we built it like this, delta pi. So it depends upon this transition matrix, these numbers P and Q. It depends upon the initial distribution I. It depends upon this this measure, this product measure that I had. So this is my random simplex that I'm building, my random limit of simplices, and this is the projective limit of these delta y n's, and then psi n's, going from delta yn to delta yn minus 1. So where, as I said before, psi. IN is the base inclusion. If I'm going up in dimension from yn to yn minus 1, so if yn is yn minus 1 minus 1. So if in my chain I went down position, or plotting up or a plotting up chosen randomly according to mu. To mu, and the opposite is true. Yn is yn minus 1 plus 1. If I jump up. Right. So this with this I have a probability distribution on simplices, and this gives me our so then we build this, and then we construct the associated in this terminology that I introduced this discussion, strongly deconstructible.
And if it so happens that yn minus 1 is just equal to yn minus 1, I'm sorry, simply yn, what am I trying to say? Is that your next step,
Yeah.
yn, imagine it's just equal to, it cannot be, sorry, it's always different, sorry.
Exactly. I mean, yeah, it's the way I've set it up, it's these describe the possibilities. It's either one more or one less. But as I said, I could allow for more variations of this.
No, but wait a second, so imagine that yn minus 1 is 5.
Yeah.
And yn is 4.
Yes. So that means I'm in this situation.
Yes. Okay, so it's 4 to 5, yes, okay.
So then I
Yeah.
embed 4 simplex in the base of the 5.
Yeah.
Then remember this terminology is strongly deconstructible, which just meant that the K0, the ordered K0 group and the K1 group is the same as the complex numbers. So the only part of the invariant I had to play around with was this trade part, which I've now put a probability distribution on. So now we are going to finally address the question, which was what is the probability that is isomorphic to the geometrical algebra, given that A is one of these guys. A and E is strongly deconstructible. That's what I set up as my questions. Okay, so let's apply the answer. Okay, the answer will depend upon these things, I and mu potentially. In fact, I mean, because of this theorem here, the little pi is not what's important. What's important is the capital pi. In other words, if the walk is transient, that means that my dimension of the simplices is steadily going to the probability 1, steadily going to march up to infinity. On the other hand, if I am in the recurrent case, q bigger than or equal to p, then I'm going to keep going back to 0 all the time. I'll go far out, and then I'll come back to 0 again and again and again. So I'll keep returning to low dimensional simplices infinitely often in seconds. And then, of course, it also depends upon this mu, the choice of collapsing. So let's see what answer is there. Okay, so first of all, if Q is bigger than or equal to P, that means that I'm in this current situation, then the probability is 1. Maybe okay. The probability is 1. So in other words, I just don't want to keep writing the same thing over again. This probability is the probability that this random strong K contractible algebras isomorphic to the Jacelon, or is in almost isomorphic. Secondly, if P is bigger than Q, then almost surely, meaning the probability 1. As I said, the walk tends to wander off to infinity. So the dimensions of the simplices is going to grow ultimately. So almost surely the dimension of the trace space. The dimension of the trace space of A.
Am I right in thinking that saying probability 1 and is equivalent to almost surely is because you have sets of measures 0, right?
Sure, yes, yeah. I mean, yeah, it is the
Because in say some colloquial English, you'd say, oh, it's probability 1 is going to rain. This thing is for sure it's going to rain.
Yeah, but yeah, that's a good point. But I guess this is the sort of accepted problem terminology in probability. All right. So dimension of the trace space is going to the dimension of the trace space is infinity, and that's just determined by what's happening in the transition matrix. But if we pay attention to the collapsing points, the random collapsing points that we chose, we can even say what kind of simplex we get. In fact, in case 1, okay, case 1 was the case where I had maybe let's go back where I can use the cases. Yeah, I had 3 possibilities for these measures. The first case was I had no probability at all as far as the collapse points are concerned. It's just all the time I demand that I collapse center of mass of the simplex. And I know in this, the theorem that I was in the middle of writing, I'm in a situation where I'm transient walk. So I know that the simplex is with almost surely going off to infinity. So the only question is what kind of simplex do I get? And in this, if I demand that this is the collapsing point, what I will get is in fact a Bauer simplex, meaning the extremal boundary is compact, and it's sort of the simplest possible Bauer simplex. The boundary is homeomorphic to a convergent sequence. In the second case, where I'm doing this random degeneracy, Mark, is that the terminology, degeneracy? Mark? Yeah, then I will also get Bauer simplex, and that's a necessary condition of collapsing to vertices. So I'll also get a Bauer simplex, but in fact, I will get the boundary almost surely isomorphic, homeomorphic to the counter set. That's what I'll get in the second case there. And in the third case, and this is the reason that I set up this kind of delicate sampling procedure is with probability 1, I'm going to get the Boltzmann simplex. So I'm going to get the simplex where the extreme points are dense. And yeah, my first thought when I was thinking about this sort of thing was, yeah, if I just took the Lebesgue measure on just delta n for each mu n, then yeah, I probably will get the Boltzmann simplex, but that ultimately was not clear to me that that was true. It seemed to get this kind of density condition happening for the Boltzmann simplex, getting the extreme points dense, I wanted to make sure that I'm sampling every open ball infinitely often, which is what's happening with this sampling procedure. If I just choose the Lebesgue measure, then because dimensions are growing, I sort of, it's like the heat death of the universe, if you know, okay, anyway. But right, so this will give me the Boltzmann simplex. Right. So maybe I can just. So in the first case that we had no randomness at all, the trace space of A is almost surely affinely homeomorphic to the Bauer simplex. With boundary as I said, convergence sequence. So, you know, 1 over n, and Z0 is not n equals 1 to infinity, union the limits. The simplest possible, well, simplest possible infinite dimensional power simplex. Second case, this was where trait space is almost surely isomorphic to the power simplex. So with boundary counter set. And the third case is almost surely isomorphic to both simplex. 3 points of this. Yeah, I mean, I'm not going to go into the details of the proof of this, but this is just sort of proved by characterizations of the Potent simplex. So the Potent simplex, I chose this sampling procedure essentially to get the density criteria. So this is kind of by design to get the Potent simplex. The counter set is by it's by this graphical result of Brouwer that characterizes the counter set as the compact, totally disconnected space with no isolated points. And
the counter set has infinite dimension here.
So this is a good point. I mean, I'm not saying that
With the boundary.
Yeah, the boundary is 0-dimensional as a space, but this is the simplex is infinite dimensional. So the simplex is the closed convex hull. The closed convex hull of the contour is infinite dimensions. Now it's
Because here I wrote dim TA is infinity, so.
which is true. I mean, this I stand by this, but yeah, what I'm not saying is that the dimension of the boundary is infinite. That's a different thing.
I'm confused. So you write that T of A might be, for instance, counter set.
No, I'm not.
No,
It's
boundary
power simplex with boundary the counter set.
Aha, oh yes, I'm so sorry, yes,
Points.
yes,
Extreme points.
yes, okay, yeah, sorry. Mhm.
No.
That's clear.
I guess it was so clear. Whatever.
Yeah, exactly.
I mean, ditto. Power.
Yeah.
Bhishan, I don't quite follow the logic. You have 2 parts to the theorem, part 1 and then part 2.
Yeah.
But so if in a certain case, the P is strictly greater than Q, all right?
Yeah.
Almost surely, okay, that's simple enough. Almost surely the dimension of the simplex is infinite.
Yeah.
But then you have 3 possibilities. Does that mean there's some relative? Are they equally likely, or what?
Yes, just to clarify, because I have not just this. So this simplex has certain parameters that it depends on. The first parameter is this P and Q business. So that's why the dichotomy of the theorem is part 1, part 2. This initial distribution doesn't really play a role, but the Romanized the 1, 2, and 3. That's because of this choice of measure mu. So what
those are 3 specific choices of measure.
Yes.
Exactly.
I forgot.
Yeah, in principle, I guess I could choose, of course, many possible choices, but I'm only looking at 3 particular ones because I know what the answer is in these 3 cases.
Yeah. So if you look at these 3 possibilities for the measure, do you see some sort of hint of what the extreme points are going to be?
Yeah, so I mean, so for example, in this second one, because I'm this one, I'm all the time sending extreme points to extreme points at each stage. So the extreme points of the n simplex get sent to the extreme points of the n-1 simplex. And, and with probability 1 in the limit, I will get the set of extreme points homeomorphic to the counter set in this case.
And number 2, yeah, okay, yeah.
In number 2. In case 1, where I don't have any randomness, I'm not choosing the collapse points randomly, I'm just demanding that I send the extra vertex to the center, then I get again a Bauer simplex, and the extreme point set of extreme points is just a convergent sequence. Together.
Okay.
Together
Be interesting if you can give some general sort of correspondence, how the
Yeah, the thing is the theory of representing matrices is a bit difficult. I would say. I think it's in general it's a difficult problem. If I give you a representing matrix, if I give you a collection of collapse points to describe what the simplex looks like in the limit, you can say in certain special cases, which is sort of exactly why I'm choosing these special cases. In these kind of special cases, you can say what kind of limit you get. You know, the Boltzmann simplex. That's what's happening in case 3. You get the Boltzmann simplex, or this easy Bauer simplex in case 1. But sort of, I think maybe I have to remind myself, but maybe there is a characterization of when exactly you get a Bauer simplex. I think what's true is you get a Bauer simplex with totally disconnected extremal sets, precisely when you do something like case 2, where you do these kind of degeneracy maps. You insist that you always send vertices to vertices. In this case, we would have no choice but to get a Bauer simplex with totally disconnected boundary. So the only question is whether I have any isolated points. And because I'm choosing the uniform counting measure on all of the vertices, or the possible vertices I can collapse to, that's why with probability 1, I will get the counter set. If I had chosen not the uniform measure, but some sort of weighted thing, then I could potentially get, I guess, any Bauer simplex with totally disconnected, with 0-dimensional boundary. But it's an interesting question. I guess I did think for some time, but I didn't really get anywhere whether you could characterize, when you get an n-dimensional boundary for some n rather than just a 0-dimensional case. I think that would be an interesting question if you could come up with some characterization of getting an n-dimensional boundary, but I don't know the answer.
Well, the Poulsen simplex comes up in an interesting way if you look at Bhishan algebras, the stable rank 1 Bhishan algebras. If they're not Jiangsu stable, I mean, if they don't put in too many point evaluations when you make the limit simple, then you get the Poulsen simplex for the trace simplex.
Okay. I guess I think I knew that, but is that how difficult is that to show actually?
Well, how do you see that?
How does one see that?
Well, it's very similar to the the standard construction for the Poulsen simplex is where you take the two-sided shift on the infinite product, for instance, just a 2-point space, and then or maybe it has to be I've forgotten what kind of space you have to have, but probably maybe just within infinite product of 2-point spaces. Then you look at the invariant measures under the two-sided shift.
Right.
And that's a Poulsen simplex. If it's, I think as long as it's just not a single point, then yeah. Well.
Okay. I'm.
And
not sure.
the Bhishan construction is remarkably similar to that. In fact, you'll recall that Gio and Kerr produced an example with similar properties to
Right.
and one expects it's going to have to be the same thing, but
But okay, right. But yeah, of course, that's not not
with some
known.
transcendental, we're using some transcendental classification.
You're right.
theory.
Right. Yeah.
But already the Wheelson algebras can be classified, given that the Poulsen simplex is not part of the invariant. I mean, the simplex is not part of the invariant because it's always the same. You just look at the radius of comparison.
Right. I mean, this was a recent result of yours and Zhuang Liu, was it? That,
Yeah, and a former student of Gui Hua's,
okay.
who's in China. No, well, anyway, it's interesting to see the Poulsen simplex come up.
Yeah. Absolutely. Okay. I mean, another area where this Poulsen simplex comes up is in this Frese theory that the modern theorists are so fond of. The Poulsen simplex, one way of describing it is it's the Frese limit of the category of finite dimensional simplices and affine connecting maps, meaning it is the generic object that can be built out of finite dimensional simplices. I guess. So I mean, but that's more or less why I was kind of interested in this sort of probabilistic construction, because there are results along these lines in Frese theory. If certain relational structures like graphs are built randomly, you build a graph by deciding whether to draw an edge between any two vertices by tossing a coin, or you decide whether two generators are related or not by tossing a coin. And then there are results that say that with probability 1, you will get the Frese limit of the category in which you're doing this construction. So I was generally I was trying to see whether you could do something similar in the C-star setting, whether with probability 1 you could get the things that we kind of expect are generic in some sense. And by the way, the Jiangsu algebra is also can be described as one of these Frese limit things. Anyway, that's just why this was sort of on my radar.
Oh, thank you.
All right. Let me. Okay, so I think I was.
Sorry, could you come back to this previous page?
Which page?
This. So this criminal limit is in which category? Where are these measures?
So this inverse limit is it is a metrizable showcase simplex. So it is in the category of
It's my object. You make system below.
Yeah.
There's no measure here. So
There
you are
is-
fixing measures.
I'm fixing a measure, but the mu n, maybe I should put a mu here because this mu does affect. Remember, if if I'm going down in a dimension, then I choose this pi n randomly according to the measure mu. So the mu n is implicit in the definition of these psi-n's.
Psi-n's, they were mappings.
Yeah, psi-n's are mappings.
Where are measures? What's the relation between psi-n and mu n?
So remember, psi-n. Yeah. Okay, so if this, let's say if this simplex is one dimension bigger than this simplex, psi-n is a collapsing map where it fixes the base and sends the extra vertex somewhere in the middle.
Yes.
This vertex somewhere in the middle is determined by mu n's. So the mu n is a measure on simplices. Mu n is a measure on this this target simplex.
Yes, and there is no relation between psi-n and this mu n.
Well, I mean, there is a relation in the sense that the map the point that I collapse to is chosen randomly according to mu n.
The property of this system,
Yes.
that these maps, in a sense, are random. Because
Yes.
it is mu n.
Yeah, absolutely, absolutely, yeah, the run, yeah, so it's,
Okay.
yeah, exactly,
So
exactly.
its relation is this randomness.
Yeah, that's it.
But still mu n is missing.
Yeah, I mean, I guess it's sort of implicitly in this description here, but you're right, I guess
That's a yes.
I should include it in the notation.
Inverse limit should be the object of the same category.
Yeah, sure. Yeah, okay, I don't know,
You mean tuples, I mean, a pair cannot collapse to a triple. I sorry.
Preservation.
yeah, okay, I mean, I take your point, but I hope it's clear now.
Yeah.
That's what I mean by that. All right, so maybe I just, yeah, all right, so just, okay, so the statement of theorem was, okay, so if I'm in the transient case, no, sorry, this is the recurrent case, so Q is the probability of going this way towards the origin. So if I'm more likely to head home than I am to head out, then I will, with probability 1, get the jump to algebra. This is the case just for kind of a silly reason. It's because the probability 1, in every state is visited infinitely often. So in particular, the 0 state is visited infinitely often. So infinitely often I come back to 0. So infinitely often I come back to the 0 simplex, in other words. And the inverse limit, the projective limit that I'm constructing is the same as inverse limit over any cofinal subset. So if I'm visiting the 0 simplex infinitely often, that means I have a unique trace. So I'm constructing almost surely a limit with the maps trace collapsing.
Because 0 is initial.
Because 0 is initial, yeah, exactly. So it's just sort of for silly reasons. This I'm getting a unique trace because I'm visiting the unique trace simplex infinitely often. This case there.
Sorry, can you remind me how this random walk determines your C-star algebra A? Just I noticed.
Yeah, so right, so it's A. So the random walk is giving me I'm thinking of my positions on the walk as the dimensions of the simplex.
Yes, so I have a simplex.
This random walk,
Yes.
therefore gives me this sequence, these
Of map signs.
between finite dimensional synthesis.
Yes.
I use the sequence to build a limit, a projected limit of finite dimensional synthesis. And then I identify the unique classifiable object.
I've got you. Yes, it's beautiful.
Yes.
Okay.
That has the easiest K theory that I can manage, and this random simplex as its trace.
Okay.
Only this trade part.
Yeah.
Everything is hidden in classification.
Yeah.
Yes.
It's exactly why I'm calling this an application of classification.
Yeah.
It's how I'm making sense of the notion of random.
I needed to have it repeat.
That's fair enough. Okay. So okay. So that's why I have this holding in phases. This kind of silly reason I'm visiting 0 simplex infinitely often. And then the second case, I guess we've talked about a little bit now. So we're in the transient case here, with probability 1, I'm wandering off to infinity. I'm tending to go out more than I am to go home. And then just by okay, if you wanted to go through the full details of the proof of this, it depends upon the theory of representing matrices, but there are the characterizations that I mentioned. If we're in the second case where we are sending vertices to vertices, then I have to get power simplex with totally disconnected extremal boundary, and then because I chose things with the uniform counting measure, that's why the probability 1 will get the Cantor set. And then the third case, it's just by design, I chose the sampling procedure so that I
have a question.
Yeah.
So in the second case, you have this trichotomy. It looks like a trichotomy, but maybe it's because you were able to invent 3 types of these measures.
Yeah. It's a false trichotomy.
False trichotomy.
It's fake. Yeah, absolutely. These are here are 3 cases where I know the answer.
Okay.
Yeah.
But if some expectation.
Yeah.
Is this expectation motivated by the fact that you know on the right-hand side what would be almost surely this trace space?
Sorry,
Is there a trichotomy on the level of on the right-hand side?
No, definitely not. No, I mean, these are very, very special.
So these are very special cases.
Yeah, absolutely, very special cases. In fact, these are sort of like the only cases where we can actually say something concrete about. You know, the syntheses are very wild potentially. You can, you know, especially if we're outside in the Bauer simplex case, unless we are so wild that I'm sort of generic and I get the Paulson simplex, then it's very, very difficult to say what it looks like. Very, very difficult. So that's why I'm getting it. Absolutely false trichotomy.
So these are like lucky, three lucky shots.
Yeah,
in this mysterious area.
yeah. Yeah, absolutely. I guess I would argue that this case too is quite natural, I would say. That's where I demand that I collapse this extra great X to one of the base vertices uniform. I think that's quite a natural thing to do. So I would argue that at least this case is if I had only said this case and not mentioned the other two, I think I would be at least somewhat content with that because it's a natural thing to do. This is almost natural, but it's a little more delicate than one might like. But still, I think for similar reasons, this is also a somewhat natural thing to do. I mean, this is okay, maybe this is natural in the sense that this is when I decide, okay, I don't want any randomness of collapsing ones here. So yeah, they're not. They're three special cases, but they're not such like out of nowhere, outlandish things to do.
But none of these cases is generic in the sense of previous talk, I suppose.
Yeah, no, I guess not. I guess not because this is because it very much depends on this choice of measure. So it would be it's difficult to even formulate.
For genericity.
Yeah.
This choice of these measures would matter.
Yes. But I would contend that I'm setting up a different notion of genericity here. So this today is about probabilistic genericity, in which case we're talking about whether things happen with probability 1. So which is a different notion to the notion of genericity in a Polish space, which is what we had on Wednesday, whether things are happening on a dense G.
But I'm talking about genericity of these properties, like Bauer simplex, boundary, blah, 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 also simplex.
In the sense of Wednesday, you mean in that?
Yes.
Yes. So being a dense G delta in.
If you imagine trace spaces.
So simplices, kind of simplices then. Yeah.
Synthesis.
Yes.
So what is your expectation for it?
I see what you mean. What is the generic simplex?
Yeah.
Yeah. That's.
Is Paulson?
Yeah. Okay. So I again, if you're talking about generic in the sense of density delta, I don't know. I'm not even sure. You know, my instinct.
Okay, loosely speaking, typical.
So if you interpret generic in the sense of Fresnel theory, which is a sort of precise way of saying that the generic structure that can be built from its finite dimensional substructures, which are these finite dimensional simplices, then the answer is yes, it is
the third one is typical.
Is the generic simplex in the sense of Fresnel theory, I think, yeah.
So first case is probably very finished.
Yeah.
The second is something more general, but still not general.
Yeah. I would say so. Even being a Bauer simplex, I think is very, very special. Having a closed extremal boundary, I think is very special. So generically, you would expect your simplex to not be a Bauer simplex. Lower, I guess. So it's a little bit more general. It's maybe if you restrict your attention to Bauer simplices, maybe this is some kind of
So counter set, boundary counter sets is generic for power simplicity.
Maybe.
Too far.
I don't, yeah. But yeah, it's fun.
Yeah, but to understand the geography of this
Yeah, sure.
free spaces,
Sure.
lot of questions.
Yeah, I would say that there's this paper by, so, you know, a lot of the foundational work on representative matrices and simplices, it's in this paper of Lazar, Lind, and Strauss, where they have, you know, this characterization of the Boltzmann simplex, for example, among other things. But there's also this paper that I found that I found it very illuminating. It's by this guy, Sternfeld, you know, back in the 70s or 80s or something. I can't remember exactly when, but it has a lot of these kinds of characterization. So a lot of the theory that I got for this is in that paper of Sternfeld. And he's the one who makes the point that outside of these kinds of special cases, it's quite difficult to see what's going on. But I do think there is a lot of scope for these kinds of questions. I think, yeah, I would say I would be very interested to know whether one can characterize being a power simplex with the boundary being n-dimensional rather than zero-dimensional. I think this is very interesting.
But do you have examples of these power simplices with zero-dimensional extremal set?
Yeah.
But different from these two extreme cases. There's one accumulation point and counter set.
Yeah, I mean, sure. I mean, you if you want to borrow a simplex with this, you just take any.
If they come from some well-known cases.
Yeah. I mean, so there is a canonical way of getting a borrow simplex. You look at the trace space on continuous functions on X. So you just take X to be compact, zero-dimensional, but you make it have some isolated points, maybe with isolated points.
Can you take X to be the counter set?
Yeah, so if you have no isolated points and you get the counter set, then you get the power simplex that I described there. So this is a power simplex.
On the boundary, you can have everything.
Yeah, exactly. So whatever you want, you can have on the boundary. Yeah, and then you can build, in fact, a classifiable C-zero out of this by taking an inductive limit or something. Right. Yeah. Okay. I mean, this is more or less all I wanted to say about this. I'll just say maybe in closing is that, as I said, in this particular setup, I demanded all the time that this zero was a reflecting barrier, but
It's like a whole horizon.
right. But if instead I allowed for this reflecting absorbing state,
So -1 is like.
-1 is like the black hole. Yeah, exactly. If I put a black hole that's -1, then and I took the dimension of the simplex to be the highest point that I reached, then I can in fact compute the probability that I get a finite dimensional simplex as my trace space with at most k extremal points. It's a computable probability. The way you can to compute that probability, you can set up a drunkard's walk problem. So you imagine you have a bar at position k, and you have the home of drunkards at position -1, and the probability that you have less than so the drunkard stumbling back and forth. If the drunkard ever reaches the bar, they stay at the bar. But if they ever reach home, they stay home. So the probability of getting, getting less than k states, less than k extremal traces, you can interpret that as the probability of the drunkard eventually going to bed. This is a computable probability. Right, but I mean, I know it's a little bit early, but really this is all I
Okay, thank you so much, but let's use these 5 minutes for some final thoughts or questions. Tomek?
Yes, I have a question.
Sure.
Could you come back to the definition of these three cases?
Yes.
Three choices of these measures.
Yeah.
Yes. So you could think about these simplices as measure spaces, probability measure spaces of finite set.
Sure. Yes.
Okay. So this gives you a different probability dimension.
Yeah.
So on such simplices, there's a function which is called entropy.
Yeah.
Entropy.
Yeah.
Okay. Measuring how concentrated is this measure. Okay.
Yeah.
So if you consider such systems, you could ask what is happening to this entropy.
Yeah.
Okay?
Yeah.
So for instance, in the first case, if you have some vertex, after this transformation, of course, at vertex, the entropy of this vertex is the measure concentrated at this vertex is 0.
Mhm.
Okay, but this middle point has maximal entropy. So in this first case, it's something like transforming something of entropy equal to 0 to the case of maximal entropy.
All right. Right.
In the second measure, I don't understand this well. What is happening with respect to this
Yeah.
growth of entropy?
Yeah.
In this first system, the first system is a system of a maximal growth of this entropy. The system number 2, something is happening to this entropy. I don't understand, but I would like to understand very much. And this third case about this normalized Lebesgue measure, but this, where is this? Okay, I see. So these are measures on this set of measures. But number 3 says nothing about these vertices. Can we say what is happening? Yeah.
Yeah.
Where is this map? It's about the measure.
Yeah. So I'm describing, in fact, a sequence of them. So I'm saying mu Sn plus 1 is the measure, the normalized Lebesgue measure on delta n. And then mu Sn plus 2 is the normalized Lebesgue measure on the base of it. And then
so the choice of mu is like the choice of randomness of some measure. If you interpret the point of delta n.
Yeah, right. Right.
Okay.
Yes.
So there are random measures. And
yes.
Then you have some transformations of this which must do something to this entropy, which is defined on this simplices, but I don't understand what is happening in 2 and 3.
Yeah, no, it's a very interesting question. Yeah.
Okay.
Yeah, I know, and this is it's a good. Honestly, this is something that I mean, not exactly this, but entropy is something I do have on mind. So yeah, think about this.
Black hole horizon entropy.
Thermodynamics of black holes.
Right.
Beginning to make sense. Okay, now please correct me if I'm wrong, if I'm somehow understanding you properly. So you have this Elliott invariant to classify a certain class of sister algebras.
Yeah.
And bang, there is a Jankshu sister algebra, and the invariant is equal to that of a complex number. So it cannot classify to this invariant. So now you are posing, from this point of view, a very natural question, right? I'm constructing some sister algebras, okay? And I wonder with what probability it is isomorphic to Jiangsu sister algebra,
Yeah.
provided that this construction somehow depends on some things, right?
Yeah.
Do I get
Yeah.
it correctly?
Yeah.
This is the picture.
Yeah, absolutely.
Okay.
I mean, so in the paper where this appears, I did several different random constructions. So one is along these simplex construction of Jiangsu-like objects.
Mhm.
Another one was random UHF algebras, which I spoke about a couple of weeks ago. Also, the random graph algebras also appears in that paper, and I do also look at these random Wilson type algebras that George mentioned, and you get this thing that George also mentioned called the radius of comparison that becomes a random variable. So but yeah, the basic question is there are all these constructions that are quite sort of central to providing models for classifiable C-star algebras, and I'm just all the time posing the question, all right, what if we take that construction and make random choices instead of deterministic ones?
Yes.
Ask what you get.
Last time you were talking about some wider variant.
Yes, for classifying morphisms.
Yeah.
Yes.
Can you compare this randomness of algebras and randomness of these morphisms?
Yeah, it's a good question. It's a good question. It's a good question, and I don't have an immediate answer. I don't know, but yeah, good and necessarily more difficult question.
Next step.
Yeah, I guess.
Okay, George, if you don't have any questions or comments, I will close this mini course. Last chance, final boarding.
Oh, thank you.
Any questions, comments? No. So in this case, let us say a big fat thank you to Bhishan, because he was lecturing for 2 weeks, which means 12 full hours of lectures. He gave another 2 talks at our conferences, one for students, one research. So it's altogether 14 hours of sheer talking, and it was worth every penny. I mean, we are delighted. So please say big thank you to Bhishan for his great work. Thank you so much.
Thank you.
Okay, so I'll stop recording.